I'm not saying that you will get this right away. What you will get is an exponential of x square minus x square or something. When you normalize it, you would get the stars. How do you normalize it? The formula is very simple. You have e raised to minus ax square dx minus infinity to plus infinity is nothing but square root of pi by 8. That is means that you have to use it. In fact, at a later stage, you will use the other formula. Okay. You use the fact that if you have x square e raised to minus ax square dx 0 to infinity, say this is equal to 1 over 4a. Might want to keep this in mind if it's right. Okay. Or you can look it up. How about this term now? What do I do about it? So what I can do is, I take this dp22 by dh2 and transfer it on this side. Okay, take the p11 on that side. So once again, you would get that one side is dependent only on 2, 2, and the other side is dependent only on 1, 1. And lo and behold, if you carry the argument out further, you get that P11, H11 is equal to, I think it's C by 4. Just give me a minute. You put E raised to minus C by 4, H11 square, with an appropriate normalization, which I think is C by 4 pi square. So the upshot of this exercise is very simple. You get the Gaussian distribution. And you get this Gaussian distribution by making a very simple approximation. Basically, that the probability distribution should be invariant under a unitary transformation. I think it is brilliant. It's very good. I would say it's a very nice theoretical physics. You don't have to make any serious assumptions. No, I remember the question that was asked when the introduction got over. I said, what are these what is varying? Because let it vary any way which it wants. Let the H11 vary whichever way it wants. As long as the probability distribution is uncorrelated, okay, and as long as it is invariant under a unitary transformation, I will get a Gaussian.
So,
yes.
So this is John. So in the above equation where you have separated it out as two constants. So where did the terms P22 and P11 go? I couldn't understand it.
No, I don't understand the question.
No, I don't understand where the terms P11 and P22 went.
Yes. Well, can I erase them? Let me see. I mean, I thought I've done this quite correctly. It's over. I mean, there's nothing to do now. There was like 2H11, huh? Where is that? Yes. So what is the doubt now?
So,
I don't know what the doubt is now.
So in the second and third term, there's a P22 and P12 in the denominator, right?
Yeah, no, P11 be an answer. There, in the previous term. Correct, it's there. It will come. So you just think about it, there is no hanky-panky, there is nothing wrong here. It's just that I forgot to carry over this P11 and P22. Is that clear? So sorry about
Yes.
that.
But sir, I'm asking the same question as before. But if you don't know what is causing the randomness, how can you talk about whether if it is correlated or not?
No, we are making that assumption. No? I'm not saying that it is not. If it is uncorrelated, then this will happen. If it is correlated, it won't happen. If it is
Okay.
correlated, something else happens. Okay, then you have to make a model about what kind of correlation. Is 1 correlated with 2 only and not with 1 or not?
Hmm.
To make some model, and people have done that also. Okay. This is beginner's work, the very first piece of work that he did. Okay. Then people like Dyson, Mehta, etc., relaxed it to a certain extent and went further. But once you assume this uncorrelation and invariance in the unitary transformation, you will get a Gaussian. The pH then becomes, let me write it down, C by 4 pi square root e raised to minus H11 square C by 4, correct? Similarly, you get C by 4 pi square root e raised to minus C by 4 H22 square. I'm just writing it so that you are reminded about this. C over 2 pi square root e raised to minus C. Random matrix theory. That is how the matrix tensors change. That is not to say that that is how the eigenvectors will change. Next question is, what is the distribution of the eigenvalues, not the eigenvectors? We can do the eigenvectors also, but let's do the eigenvalues first. Distribution. Okay. Here we enter a domain that is slightly more complicated, but still manageable. What are the eigenvalues? One is the bonding, we'll say one is anti-bonding, E alpha. Alpha standing for anti-bonding. That would be H11 plus H22 by 2. That is the epsilon bar that you saw in the introduction. Plus 1 by 2 H22 minus H11 the whole square plus 4 H16 square. That would be one of them. What would the other one be? It would have a minus sign, and that would be that I would call as beta bonding. So the two eigenvalues. Fair enough. You can also show a certain relationship between the eigenvalue between this and between E alpha, E beta, and H11, H22. What you could show is that if I took the E alpha square and I took the E beta square, take the square and take the square. So if you square it, this will become simply H11 square plus H22 square plus 2. Take this and you square it. If you square it, this becomes square, this becomes square, and you get a term like a cross term. If you take the minus sign, the cross term will cancel out. Is that clear? Because there is the beta square, and there is the alpha square, so the cross term would cancel out. And you'll be left only with this. And now you compare it with what you have over here. Okay. So if I am interested in this probability distribution, E alpha E beta. And it also depends on something called theta that I will explain in a minute. Okay, so just hold your horses till I explain that. But if I'm interested in this, I will get something here which I don't know. Right? But I will also get, because of the fact that this is C by 4, and this is C by 2. Okay, please pay attention to that at the blackboard right now. Okay, at this board. This is 1 by 4, and then 1 by 2. So this is that 2h12 square. Okay. So what you would get something which I will come to later, but you certainly get something like this: E alpha square plus E beta square into minus C by 4, I think. But let me check the number. Whether it's 4 or 8 or whatever. You will get something. What about the prefect? What are you going to get before that? It is not as simple as it looks. Okay. Because this is separable. It is like saying they are uncorrelated. But if you look a little deeper, they are not that uncorrelated. What you would get over here is a very, very interesting term, which is E alpha minus E. How that arises, we will come to in a minute. But you'll get a term which is the difference of the eigenvalues or the band gap term. And what you get, the rest of it is simply a normalization. This I have not explained. This part is sort of obvious, it's staring you in the face. So let me, in the next 10 minutes, first of all, let me tell you what is the physics behind this right now. And then after that, time permitting, tell you how to get this. But first I'm more interested in getting to the physics of this, and then to the dynamics which gets this. If you want to transform one probability to another, you have to use, you can do it provided you calculate the Jacobian. And the Jacobian calculation gives you this, E alpha minus E beta. I haven't done it. I'll tell you how it is done. But first I would like to jump ahead and tell you what the physics is. Assuming that this is correct. Okay. Okay. And admitting the fact that I have not derived this yet. I can certainly claim now that P, E alpha, E beta, and then the theta which I'll come to in a minute, is not equal to. So the theta just drops out, but then it doesn't equal this. So it's not uncorrelated. So even though the matrix elements are uncorrelated, this thing is not, the probabilities are not uncorrelated. So that is one. The other is, okay, that the second point I would like to make is that very interestingly, this P, this quantity depends on E alpha minus E beta. That is to say, it depends on what I would call as the level spacing. You can call it anything you want. You can call it the band gap or the Lomo-Homo gap, etc. But it depends on this. Okay. And the third thing would be that I began with a C, which I could only claim was an arbitrary positive number. Now, and again, this expression allows me to actually put some physics into the C. But before I do that, it is clear that you have something like a Wigner distribution. You already have an E alpha minus E beta. So I jumped the gun. I will, instead of trying to explain the step, okay, and getting trapped in it, let me first see what is my distribution if I were to ask the question, what is my P of epsilon, where epsilon is equal to P alpha minus E. What is this quantity P alpha mean? If I'm not interested in alpha and beta separately, but I'm interested in this difference, okay, then this quantity by mathematics, okay, is nothing but integral P alpha. That is this expression over here, okay, into delta of epsilon minus. That is the definition of how you get this probability distribution. One more step. What is E alpha E beta? It's nothing but this. And this is nothing but a delta function. Okay. So let me rewrite this as epsilon minus epsilon alpha, say plus epsilon beta minus E alpha. E plus E beta minus E alpha. And integrate over E alpha. If I integrate over E alpha, wherever I see an E alpha over here, I would simply write it as E plus E beta the whole square. And this, of course, is tailor-made to give me just epsilon. So I will get, forgetting the factors, I will get an epsilon, where epsilon is this difference, E alpha minus E beta, okay, into integral E raised to minus C by 4 E beta square minus C by 4 epsilon plus E alpha square E beta square. Perhaps I've gone a little too fast, so let me pause for a minute and then explain these steps again. People always wonder this random matrix theory and this kind of a Wigner distribution that we will now get. I mean, there's a very central role in quantum chaos. If you have done some chaos theory, particularly some quantum chaotic theory, then people say if you have a non-integrable system which is ergodic, that is, energy is conserved, then you will get this Wigner distribution. So there are other ways of getting this distribution. I have done what is called probably the simplest possible way to get to this distribution. So, to just give you a flavor of what it is like in quantum chaos, if I have a distribution P epsilon, which is of this type, that's P raised to minus epsilon, if it is Poisson, because the system is not chaotic. If I have a distribution like this, that is epsilon P raised to minus epsilon square, which is the Wigner distribution, okay, it is ergodic and non-integrable. And then you get other kinds of distributions which are of the type epsilon to the power of beta, E raised to minus epsilon square, where beta is equal to 2. Where even time reversal invariance is broken. So all these level spacing arguments that arise interminably in quantum chaos, okay, arise from this kind of a discussion of the level spacing. In my language at least, I'm not interested in level spacings per se, I'm interested in a very simple thing. What is the homo-lumo gap? for a random collection of molecules. Okay, or what is the band gap? So let me explain the steps. I have a distribution over here. This is certainly not, where is it going? This is certainly not of a separable type. It is not uncorrelated. I'm not interested too much in that. I'm interested in the fact what is the level spacing, what is the homolumo gap. So I try to construct and get this quantity P of epsilon, which is just this distribution, into a delta function, integrated over alpha, beta, and theta. Since this theta is occurring repeatedly and it's got no relevance here, let me try to tell you what this theta is. If I rotate something, okay, then the wave function is like cos theta 1 there plus sine theta or minus sine theta, and 2 prime is equal to minus sine theta 1 plus cos theta. It is the rotation that gives you this theta, because I'm rotating the matrix. So this theta is an angular distribution which varies between minus pi by 2 and plus pi by 2. Okay. I'll send you a short write-up about it in case you're confused. Okay. And you will be confused, but I can tell you forget this theta. When I integrate over theta, I'll simply get, if this integral will only give you a pi, then I have a freedom to either integrate the alpha or the beta. I choose alpha. Okay. If I choose the alpha, I basically have e raised to minus c by 4 beta square pulled out, and then I have this e raised to, wherever I see the e alpha, I replace it by epsilon plus e beta square. Now I can open this out. I get epsilon square plus e beta square plus 2 epsilon e beta. The beta square and 2 epsilon beta can be integrated by completing squares. That is what you standard wise do. So go ahead and do that, because that I am not going to do. In fact, I might even ask you to do it in a quiz or an exam. Okay. You can do this and pull this out, and lo and behold, what you would get. Do I have it here? No, I don't have it here. You simply get that this is equal to epsilon e raised to minus. Let me write it down. No, I don't have it. Epsilon square to I guide, there is an epsilon square here. You get an epsilon square. There is no doubt that you'll get an epsilon square. Epsilon square, what you will get? C by 8. How do I get this? This normalization will come because you have to learn how to normalize and apply this kind of function. But basically, you just square this. You get e raised to minus epsilon square, so this comes out right here. Okay. And the remaining you integrate once again by completing squares. So that is
Yeah.
Yeah.
That means only p to the power minus c by 4 epsilon square.
Minus c by 4, say that.
If you just take out the epsilon square term from there, the coefficient should be c by 4.
Oh, yes.
Argument.
But there is a rest, no? Minus 2 epsilon beta. There's one more term, 2 epsilon e beta. Yes. Right? You get an e beta, there's also an e beta square, there's also an e beta square, and you have to integrate over e beta. Okay. Keep all those terms properly, otherwise you will not get this. Okay.
So,
Yes.
so this is John. So I'm still confused on how you. Please don't rub that right side. I'm still confused on how you got the e raised to minus c by 4 epsilon a square plus epsilon b square, epsilon beta square. Yes, sir.
That comes by just h11 square plus h22 square plus 2 times h12 square. Is that correct? You take out c by 4 common or something like that. Okay. you'll get h11 square plus h22 square plus 2 times h12 square. And that's where is it gone? I written it right here. This is equal to this. How do you get this? By just examining the previous expression for the homo and the loop.
Yes.
This comes very trivially, and there's nothing like it. The difficult term is this, which comes by taking the Jacobian into account, which I have not gotten into. This one I have not explained. This is actually obvious. So I went ahead of my story because I didn't want you to get bogged down in the calculation of the Jacobian. How should I put it? A dreaded Jacobian. It is tough, not easy. But if not, I mean, it won't kill you. You can still try it. So the upshot of this exercise is if I have P of epsilon, what is epsilon? The difference between the LUMO and the HOMO. Okay, the probability distribution of this LUMO HOMO. You will get some sign E raised to minus C by A epsilon square into some quantity. I think this is C by 4, but I will just check. Okay. Yeah. And epsilon is positive, by the way. There is no reason if epsilon is going to be positive by definition. How does this look? This will look like this. What is the C? The C is a positive quantity, but I don't know what it is. Now I give a meaning to the C. The interesting thing is, I mean, it's like a complete job that you have done today. Okay. Now, nothing is left hanging loose, so to say. I'm going to interpret the C for you. I ask the following question. What is average epsilon bar? I'm interested in the average epsilon. So to get this, I will say, okay, let's calculate epsilon, P epsilon, dx. How do you calculate the average? By putting this quantity x into px dx. So you simply have C by 4 integral epsilon square e raised to minus C by 8 epsilon dx. That is the average. Okay. Let me call this as D or something. Or let me call it epsilon bar. I don't want to confuse it with that epsilon bar, h11 by h22 by 2. Okay. As long as you don't confuse it with that, this is called the mean level spacing. Mean spacing. Okay. I can integrate this. Okay. I can integrate it because I've already told you that x square e raised to minus dx square dx 0 to infinity is equal to 1 by 4a square root of pi. No big deal. So I integrate that. Do it. Kindly do it. Okay, so you try and do it, but the answer is 2 pi by c square. That is equal to epsilon bar. So now I have an interpretation for my C. What was C? C was a positive constant with dimensions of 1 by energy square. It is nothing but square root of C. That is my interpretation. So now I have a complete picture for my probability distribution. And let me write it down. It is simply equal to pi by 2d square minus I. You simply substitute for C, it's just 2 pi by epsilon bar square, you get this. Okay. Now it's completely done. This, what does this do? It's the average spacing. In terms of the average spacing, this is how the distribution looks. The Wigner distribution. There's absolutely no loose ends. Any questions? Random matrix theory. I was debating whether to do this topic because it is somewhat dense. Perhaps you might think it's a rather dense topic. But the reason I did it was because I wanted to kill two birds with one stone. While trying to address the issue of disordered systems, I also wanted to sort of expose you to a literature and to the, what is called, a nomenclature that you normally see in quantum chaos. Okay. As a description of a system which is quantumly chaotic. Okay. This is, I'm sorry, I've forgotten a very important term here, and this would be very silly of me not to put. I've forgotten that epsilon is a free factor. Okay. This is an integrable system, which is a non-integrable system, which is ergodic. So you'll see things like without this, you'll see e raised to minus epsilon there. All this are signatures of different kinds of systems whose quantum chaos, whose chaos is being probed.